Namaste students, welcome back to my channel. Students, in our previous video we have studied that how Niels Bartlett discovered the compound of xenon with the help of the ionization enthalpy, first ionization enthalpy of xenon. After the discovery of that compound, we get a number of the compounds of xenon, and today in this video we are going to study about the compounds of the xenon. Most of the compounds of the xenon are formed with the highly electronegative atoms like oxygen and fluorine, because when xenon reacts with the oxygen and the fluorine, then the sufficient amount of energy is released, which results in the moving of the electron of xenon from p to d orbital. So in this video we are going to study about the various compounds of the xenon. So without any delay, let's get started. First, we'll talk about xenon fluorides. That is when xenon reacts with the fluorine, then what are the different fluorides we get? So when xenon reacts with fluorine, we get three different fluorides. XeF2, XeF4 and XeF6. These are prepared by the direct combination of the xenon and the fluorine, but under different conditions we get different products. So Xe reacts with F2. When excess of Xe reacts with F2 at 673 Kelvin and 1 bar pressure, then we get XeF2. But when this Xe and F2 are present in 1:5, when Xe and F2 are present in 1:5 and the temperature is 873 Kelvin and pressure is 7 bar, then instead of XeF2 we get XeF4. And when Xe and F2 are present in 1:20, the temperature is 573 Kelvin and the pressure is 60 to 70 bar, then we get XeF6. So the fluorides of xenon are prepared by the direct combination of the xenon and the fluorine, but by changing the condition we can get the different products. This XeF6 we can also prepare by reacting XeF4 with O2F2 at 143 Kelvin. When this XeF4 reacts with O2F2 at 143 Kelvin, then also we get XeF6 plus O2. So the main source of the formation of the fluorides of xenon is the direct combination of this xenon and the fluorine under different conditions. Now, if we talk about the properties of xenon fluorides, XeF2. If I talk about XeF2 is soluble in water. The XeF2 is soluble in water and undergoes slow hydrolysis to evolve O2. But if I talk about XeF4, XeF4 reacts violently with water. It reacts violently with water and undergoes disproportionation reaction. Disproportionation reaction to form Xe and XeO3. Disproportionation reaction to form Xe and XeO3. So XeF2 is soluble in water, but it undergoes slow hydrolysis to evolve O2. XeF4 reacts violently with the water and it undergoes a disproportionation reaction to form Xe and XeO3, which is an explosive compound. Whereas this XeF6, it also reacts violently with the water. And undergoes slow hydrolysis with atmospheric moisture. to form XeO3. To form XeO3. So first, that is XeF2, it is soluble in water and it undergoes hydrolysis with this water only. XeF4 violently reacts with water but it undergoes disproportionation reaction. XeF6 also reacts violently with the water but it slowly undergo hydrolysis with atmospheric moisture. Due to the atmospheric moisture, it undergoes slow hydrolysis. And if I write the reaction of all three, then the first reaction becomes XeF2. It reacts with water. This XeF2 reacts with the water, and when this XeF2 reacts with the water, we get Xe plus HF plus this Xe plus HF plus O2. There is an evolution of O2. When XeF4 reacts with water, when this XeF4 reacts with water, it reacts violently with the water and it undergoes disproportionation reaction to form Xe and XeO3 along with HF and O2, and XeF6, FCH6 if reacts with 3 molecules of water. XeF6 if reacts with 3 molecules of water means when there is complete hydrolysis of XeF6, then it forms XeO3 plus HF. But when this XeF6 reacts with 2 molecules of water, then it forms XeO2F2 plus HF. And when this XeF6 reacts with 1 molecule of water, then it forms XeOF4 plus HF. So these reactions are the complete hydrolysis. Means if there is a complete hydrolysis of these fluoride, we get these products. But these two are the partial hydrolysis. Similarly, when there is a partial hydrolysis of XeF4, then we get XeOF2. Means if I write the reaction, the partial hydrolysis of XeF4 results in the formation of XeOF2 plus HF. If there is a complete hydrolysis of XeF4, then we get Xe plus XeO3. But if there is a partial hydrolysis of XeF4, then we get XeOF2. So these fluorides of xenon reacts differently with the water. Other properties are all the fluorides, all the xenon fluoride, whether XeF2, XeF4 or XeF6, all the xenon fluorides are colorless crystalline solids. These are colorless crystalline solids. These acts as a powerful oxidizing agent. For example, when XeF2 reacts with HCl, then it forms Xe plus HF plus Cl2. So here Cl is -1 and here Cl2 is 0. So -1 to 0 means there is oxidation. So therefore XeF2 acts as a powerful oxidizing agent. Similarly, suppose XeF2 reacts with CeSO4 whole thrice, Ce2SO4 whole thrice plus H2SO4. Then we get CeSO4 whole twice plus Xe plus HF. So in this way, here it is +3 and here it is +4. So Ce plus 3 get converted into Ce plus 4. That's why it is an oxidation reaction where XeF2 acts as an oxidizing agent. Similarly, XeF4, when XeF4 reacts with Ki, then we get Xe plus Kf plus I2. So these reactions prove that the different fluorides acts as a powerful oxidizing agent. Instead of powerful oxidizing agent, these fluorides also act as a good fluorinating agent. Also acts as good fluorinating agent. Good fluorinating agent. Good fluorinating agent. For example, if I write certain reaction like XeF2 reacts with NO to form Xe plus NOF. So there is addition of fluorine, that's why it is a good fluorinating agent. Similarly, XeF4 reacts with PT to form Xe plus PtF4, or XeF4 reacts with SF4 to form Xe plus SF6. So all the three reactions shows that the fluorides of the xenon acts as a good fluorinating agent. Now, if I talk about the compounds which contain heteroatom attached with alkyl or the aryl group, in that compounds the xenon fluorides act as both oxidizing as well as the fluorinating agent. So they'll oxidize or fluorinate the heteroatom which is present with the alkyl or the aryl group without affecting the alkyl or the aryl group. So here they act as an oxidizing agent, here they act as a fluorinating agent, but in those compounds in which we have heteroatoms attached with the alkyl or the aryl group, in those compounds these act as both oxidizing as well as the reducing agent. So the next property acts as both oxidizing and fluorinating agent. Fluorinating agent. So here what happened when XeF2 suppose reacts with CH3I, then we get CH3IF2 plus Xe. So here there is addition of fluorine in the compound, therefore they act as a fluorinating agent. And if I talk about the oxidation of iodine here, the oxidation of iodine here and here is different. So that's why they behave as both oxidizing as well as the reducing agent. Similarly, suppose XeF2 reacts with C2H5 whole twice S, then we get C2H5 whole twice S F2 plus Xe. Here also they results in the oxidation of sulfur and the addition of the fluorine along with the sulfur. So in these compounds they oxidized and fluorinate the heteroatom without disturbing the alkyl or the aryl group. Now the next property is they react with the fluorine donors to form the anionic species, and they react with the fluorine acceptors to form the cationic species. For example, XeF2 when reacts with PF5, XeF2 when reacts with PF5, then we get XeF positive, PF6 negative, because here PF5 is fluorine acceptor. So with fluorine acceptor they convert into cationic species. And if I talk about XeF6 plus NAF, now NAF is fluorine donor. So with fluorine donor they convert it into anionic species. So they reacts with the fluorine acceptor. They reacts with the fluorine acceptor to form cationic species, and they reacts with the fluorine donor to form the anionic species. So these are the various properties of the xenon fluoride. Now we will talk about xenon oxides. Means when xenon reacts with the oxygen, then the binary compound we get are known as xenon oxide. Now xenon basically form two types of oxides, XeO3 and XeO4. Xenon forms two types of oxides, XeO3 and XeO4. Now XeO3 we have studied that during the hydrolysis of XeF4 and XeF6 we get XeO3. So XeO3 F4 when undergo complete hydrolysis, it form Xe along with XeO3 plus HF plus O2. So here we get XeO3. Similarly, XeF6 when undergo complete hydrolysis, then we get XeO3 along with HF. So we get XeO3 by the complete hydrolysis of either XeF4 or XeF6. But XeO4, Ba2XeO6 reacts with concentrated H2SO4 to form BaSO4 plus XeO4 plus H2O. So Ba2XeO6 when reacts with H2SO4, then it forms BaSO4 along with XeO4 and H2O. So by the complete hydrolysis of these two, we get XeO3, and by reaction between barium zinate ion and the concentrated sulfuric acid, we get XeO4. Now, this XeO4 is not much stable as compared to XeO3, and it undergoes dissociation to form Xe and O2. It undergoes dissociation to form Xe and O2. But this XeO3 is stable, as well as it is a colorless explosive solid. It is a colorless explosive solid, and it acts as a powerful oxidizing agent. This XeO3, it is a colorless explosive solid. It is a colorless explosive solid and acts as a powerful oxidizing agent. It acts as a powerful oxidizing agent. For example, when this XeO3 reacts with Pu2 positive in the presence of acidic medium, then Pu2 positive get converted into Pu4 positive. This XeO3 get converted into Xe, and here we get H2O. So this reaction proves that this XeO3 acts as a powerful oxidizing agent. Similarly, if I write the another reaction of XeO3, it reacts with aqueous alkali solution. To form HXeO4 negative, that is hydrogen zinate ion, which slowly hydrolyzed in the same medium, which undergoes slow hydrolysis in the same medium, means HXeO4 negative plus OH negative. On prolonged reaction, it get converted into XeO6 4 negative, that is perzirate ion. This is perzirate ion. So along with H2O. So this XeO3 is stable. This XeO4 is not much stable as compared to XeO3. This XeO3 is a colorless explosive solid and acts as a powerful oxidizing agent. It oxidizes Pu2 positive to PO4 positive, and when it reacts with the aqueous alkali solution, then first it forms hydrogen zinate ion, which undergo slow hydrolysis to form perzinate ion, that is XeO6 4 negative. So these are the preparation and the properties of the xenon oxide. Now we will talk about the xenon oxyfluorides. Xenon oxyfluorides means when xenon reacts with the oxygen and the fluorine, then it forms a compound, and that compound name is known as xenon oxyfluorides. So xenon reacts with oxygen as well as the fluorine to form xenon oxyfluorides, and xenon form a number of xenon oxyfluorides like XeOF2, XeOF4, XeO2F2 and so on. And the preparation of some oxyfluorides, we have studied that if XeF6 reacts with 2 molecules of water, then we get XeO2F2. Here we get one xenon oxyfluoride. When this XeF6 reacts with one H2O molecule, then we get XeOF4 plus HF. And when XeF4 undergoes partial hydrolysis, then we get XeOF2 plus HF. XeOF2 plus HF. So in this way, we get xenon oxyfluorides by the hydrolysis, partial hydrolysis of the xenon fluorides. This much we have to study in the xenon oxyfluoride. Now we will study the structures of different compounds of xenon. So we are going to study the structure of different compounds of xenon. We will start with the xenon fluorides. We will start with xenon fluoride. First is XeF2. Now the electronic configuration of Xe in the ground state is S2, P6 and D0. This is the ground state configuration of Xe, that is S2, P6 and D0. Now because two fluorine are approaching to xenon, therefore xenon required two half-filled orbitals, as a result of which when fluorine approaches to xenon, the energy which is released, that energy is used to move the electron from P to D, as a result of which in the excited state we get S2, P5 and D, P5 and D1, S2, P5 and D1. Now what happened here? These two combines with the coming fluorine, as a result of which the hybridization becomes sp3d. And in the hybrid state we get 5 hybrid orbitals. The name of these 5 hybrid orbitals is sp3d, containing how many electrons? These electrons, 8 electrons, and 2 electrons are there of the fluorine. So though the hybridization is sp3, means the geometry is trigonal bipyramidal, but due to the presence of 3 lone pair, the shape is linear. So the shape becomes XeF, here one lone pair, here one lone pair, and here one lone pair. So the shape is linear. So in this way, we will find out the shape of different fluorides of xenon. Now, if I talk about XeF4, so how many half-filled orbitals I want? 4 half-filled orbitals, as a result of which one electron from P jump to D. Then I will get how many half-filled orbitals? 4 half-filled orbitals. Now the hybridization becomes sp3d2. And I have 4 orbitals in which I have single electron. So in these 4 orbitals, the fluorine reached and make a bond with these orbitals, and as a result of which the hybridization becomes sp3d2. So because the hybridization is sp3d2, we have studied in our 11th class that sp3d2 hybridization means octahedral, but due to the presence of 2 lone pair, it becomes square planar. So the structure becomes like this: XeF4, here this is square planar, here one lone pair, and here also another lone pair. So the structure of XeF2 is linear. The shape of XeF4 is square planar. Now if I talk about XeF6, how many half-filled orbitals I want? 6 half-filled orbitals. As a result of which, 1 electron more from P orbital jump to D orbital, and I get sp3d3 hybridization. With 6 half-filled orbitals in which the fluorine occupy the position. So the hybridization is sp3d3, means the geometry is pentagonal bipyramidal, but due to the presence of this, it becomes pentagonal pyramidal. Or distorted geometry. You may write it distorted geometry. So it is like this. Here F, 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 F and F. Here I'll form one pentagon. Here one lone pair and here one fluorine. Clear? So in this way, the shape of XeF2 is linear, the shape of XeF4 is square planar, and the shape of XeF6 is distorted or pentagonal pyramidal. Similarly, we can find out the structures of the oxides also. Xenon form two types of oxides, XeO3 and XeO4. Now first, if I talk about XeO3. Now in oxygen, we have studied in 11th class that we want two bond for each oxygen for completing its valency. And out of these two bonds, one is sigma and another one is pi. And pi bond doesn't participate in hybridization. So only sigma bond will participate in hybridization. It means this Xe is attached with 3 oxygen. It means 3 sigma bond should be there. 3 sigma bond should be there. It means I want 3 half-filled orbitals. I want 3 half-filled orbitals. For 3 half-filled orbitals, the 3 electrons from P, jump 3 electrons from P jump to D. Now, in the hybrid state, what happened? In the hybrid state, the hybridization is only sp3. Why? Because each oxygen form a single sigma bond with the xenon. Single. Now these 3 are used in the formation of pi bond, but these are not hybrid orbitals. These are unhybridized d orbitals. So in the hybrid state, I get 4 sp3 hybridized, hybridized orbital, 3 unhybridized d orbital having single electron, and 2 unhybridized d orbital which are empty. Now what happened? Oxygen form 1 sigma bond, 1 pi bond. Another oxygen forms 1 sigma bond, 1 pi bond. Third oxygen forms another sigma bond and another pi bond. But these pi bond are not participated in the bond formation, therefore the hybridization is only sp3. So in sp3, the geometry is tetrahedral, but due to the presence of one lone pair, it becomes pyramidal. So the shape is Xe double bond O with a lone pair. It is pyramidal. Now, if I talk about XeOF4, so how many half-filled orbitals I want? 4 half-filled orbitals along with the 4 additional half-filled orbitals. 4 hybrid orbitals for sigma bond along with the 4 additional hybrid orbitals for the pi bond. So as a result of which, one of the electron from S jump to D, one of the electron, but still the hybridization is sp3 because only these 4 will participate in bond formation. Here I get one more unhybridized d orbital having single electron, and with this the fourth oxygen forms sigma bond, and here it forms the pi bond. So the hybridization is still sp3, but all are bond pair, therefore the shape is tetrahedral. So the shape of XeO3 is pyramidal and shape of XeO4 is tetrahedral. Now in the similar way, we'll find out the structures of xenon oxyfluorides. Now structure of xenon fluoride. Now xenon form XeOF2, XeOF4, XeO2F2, XeO3F2, XeO2F2 and XeOF6. Now I'll tell you the structure of XeOF2 and XeO2F2. Then the structure of these 4 you tell me. Clear? Now Xe in the ground state, its configuration is S2P6. Now I have to make XeOF2. Now for XeOF2, I want 4 single paired electron orbitals. Why? 2 for fluorine and 2 for oxygen, out of which one is sigma and another one is pi. It means one participate in hybridization and one not participate in hybridization. So because I want 4 single paired electron orbital, so what happened in the excited state, 2 electrons in the excited state, 2 electrons will jump from P to D. 2 electrons will jump from P to D. 2 electrons will jump from P to D. Now, out of these 4, here one sigma bond with fluorine, here another sigma bond with fluorine, here another sigma bond with oxygen, and pi bond with oxygen. So, sp3d participate in bond formation. This D will not participate in hybridization. Will not participate in hybridization. So, in the hybrid state, I get sp3d. I get sp3d hybrid orbitals, in which we have how many electrons? In which we have 4, 5, 6, 7 electrons. Clear? Now with these 7 electrons, here one fluorine, here another fluorine, here oxygen, and here another oxygen. So here fluorine sigma bond, oxygen sigma bond, and pi bond. So the hybridization is sp3d, though D's participate in pi formation. But sp3d hybridization means geometry should be triangular, pyramidal, triangular bipyramidal, trigonal bipyramidal. But due to the presence of 2 lone pair, it becomes T-shape. So the structure is Xe, here one lone pair, here another lone pair, F2 double bond O. So it is T-shape. Similarly, if I talk about XeO2F2, so how many half-filled orbitals I want? 2 for fluorine and 4 for oxygen. 2 for fluorine and 4 for oxygen. So total I want 6 half-filled orbitals. So here, this move here. So I got 6 half-filled orbitals. Now out of which one fluorine, another fluorine, one oxygen, another oxygen, and these two form the pi bond. So the hybridization is still sp3d. But here one electron with oxygen sigma bond, and here it forms pi bond. So the hybridization is still sp3d, but due to the presence of one lone pair, it is seesaw. So like this it is. Xe, here lone pair, double bond O, F2, XeO2, F2. So in this way, we can easily find out the hybridization of the different oxyfluorides of xenon. Now it is your homework that you have to tell me that what are the structures of XeOF4, XeO3F2, XeO2F4 and XeOF6 with the help of the hybridization concept. So students, that's all other compounds of xenon. Means xenon form compound with oxygen and fluorine to form xenon oxides, fluorides and oxyfluorides. So that's all for today. I'll see you in my next video with the new topics.